Right now, two Air Force officers are seated at launch consoles 60 feet underground with their hands on keys, positioned exactly 12 feet apart, too far for one person to reach both. Above them, a Minuteman III intercontinental ballistic missile, loaded and waiting. They've just received a coded authorization from the President of the United States, and in a few seconds, they're going to launch this weapon across the Pacific Ocean. But this missile isn't carrying a nuclear warhead. What it is carrying will determine if America could actually win a nuclear war. Both officers have already authenticated the launch order independently, comparing codes from separate sealed documents inside a red safe bolted to the floor. The codes matched. Now they insert their keys into panels mounted on opposite walls of the capsule, 12 feet apart. Both must turn their keys within 2 seconds of each other. Each person cannot physically reach both. That's not a limitation. That's the entire point. The Air Force designed the system in 1962 around a single principle. No one human being on Earth should be able to launch a nuclear weapon alone. The capsule itself hangs on 4 massive shock absorbers, engineered to keep operating if a nuclear warhead detonates directly overhead. The blast door sealing the entrance weighs 160 tons. Getting through it without the combination would require more explosives than a small army has. Independent air filtration, independent power generation, a bank vault buried under a parking lot. Except what this vault controls can flatten a city. And this is just one of them. 400 missiles sit in silos like this one right now, beneath wheat fields in Wyoming, cattle ranches in Montana, sunflower farms in North Dakota, each one monitored by a 2-person crew pulling 24-hour shifts underground. Roughly 45 launch control centers across 3 states, 800 officers rotating through shifts every day, 365 days a year. The Air Force calls it pulling alert. The missileers who do it call it the longest day of their lives, every single time. The only job in the military where a perfect 20-year career means you never actually did your job. The system has been on continuous alert since 1970, not one day off. And for the first 15 years, it had a security hole wide enough to end civilization. The Launch Enablement Code. The code programmed into every single missile in the arsenal was 000000000. 8 zeros. The Air Force set it that way on purpose because they didn't want anything slowing down execution during the Cold War. So for 15 years, the only things between a rogue officer and a nuclear launch were the 2-man rule, a padlock, and the assumption that nobody would ever check. Somebody checked. The code was eventually changed to a real, dynamic unlock code in 1977. Now we have this. The keys turn. The sequence is automated from here. Every silo linked to this launch control center receives the command simultaneously. Up to 10 missiles at once. And inside each silo, 80,000 pounds of American diplomacy is about to erupt from underground. But first, this missile has to solve a problem. How do you throw something the size of a school bus for more than 4,000 miles across the planet and land it within 400 feet of the target? 90 feet above these 2 officers, explosive bolts shatter the restraints anchoring the missile to the silo floor. A 100-ton silo door, 4.5 feet of reinforced concrete and steel, heavier than a Boeing 737, blows open on hydraulic rams in seconds. Then the first stage motor ignites while the missile is still inside the tube. 202,600 pounds of thrust erupting inside a concrete cylinder barely wider than the missile itself. A column of fire hot enough to melt steel, rising through a hole 12 feet across. The clearance between the missile body and the silo wall is measured in inches. The guidance system is correcting in fractions of a degree from the first millisecond, keeping 60 feet of rocket centered inside a tube that would destroy it on contact. One hesitation, one drift. 80,000 pounds of solid rocket fuel meets reinforced concrete at 200,000 pounds of thrust. The missile clears the silo in under 3 seconds. 60 feet below, the crew feels every one of them. The capsule bucks hard on its shock absorbers. 4 pneumatic cylinders designed to ride out a near-miss nuclear detonation, now absorbing the comparatively gentle force of their own missile leaving home. The sound doesn't travel through air, it travels through bedrock. A low-frequency shudder that rattles pencils off the console and vibrates your teeth. The instruments spike and settle. Both officers are staring at their panels, waiting for the one light that would mean the motor failed to clear the tube, a scenario the training manual describes in exactly one word: catastrophic. If you're standing at the Vandenberg perimeter, you don't hear it first, you feel it. A pressure wave in your sternum before the sound hits your ears. The ground shakes hard enough to trip seismographs. The exhaust plume turns the California coastline into daylight for miles. Then it's gone, climbing so fast it shrinks to a point of light before you can track it. The first stage burns for 60 seconds. The solid propellant, aluminum powder and ammonium perchlorate packed into the motor casing, is a Roman candle the size of a grain silo. The Air Force chose solid fuel over liquid rockets for one reason: solid fuel weights. No pumps, no fuel lines, no plumbing that could leak or freeze through a North Dakota winter. This missile sat loaded in an operational silo for years before the Air Force pulled it, trucked it across the country, and fired it. The propellant poured into those motors years ago is burning right now at full performance. If it wasn't, if time or temperature had degraded the fuel even slightly, the Air Force has 399 identical missiles sitting underground that suddenly can't be trusted. You light solid fuel and it burns until it's gone. You cannot shut it off. There is no abort. Once that motor ignites, the only thing stopping this missile is the ground. The silo isn't much better off. 200,000 pounds of thrust inside a concrete cylinder scorches the interior down to the bare aggregate. Launch rails warp the exhaust duct at the bottom of the tube, designed to channel flame out and away from the missile, absorbs temperatures that turns its steel lining into slag. Every test launch destroys the silo it launches from. The Air Force accepts this. A missile that works is worth more than the hole it lived in. At 60 seconds, the first stage separates and falls away into the Pacific darkness. The second stage ignites instantly. 60,721 pounds of thrust pushing the missile higher and faster through the thinning atmosphere. The third stage takes over from there. 34,400 pounds. Smaller, lighter, surgical. The first stage does the brute force work of escaping the atmosphere. The third stage fine-tunes the trajectory with surgical precision as the missile punches through the last traces of air and enters vacuum. By the time the third stage burns out, the weapon is moving at 15,000 miles per hour. Mach 23, New York to Los Angeles in 10 minutes, faster than any bullet ever fired from any gun. And at that speed, it doesn't need engines anymore. The missile is on a ballistic arc, coasting 700 miles above the Earth's surface, higher than the International Space Station orbits. For roughly 20 minutes, this weapon is just falling. An object in free fall, following the same laws of physics as a thrown baseball, except this baseball weighs several thousand pounds and is moving at Mach 23. Unpowered, unstoppable. Nothing in any country's arsenal can reliably intercept it at this speed and altitude. No GPS, no satellites, no ground stations, no radio signals of any kind. From the moment it left the silo, this weapon has been completely alone. Just physics and a guidance system that hasn't received a single signal from anyone since the moment it left the ground. Remember that. It's going to matter. The engineers who designed this weapon assumed that by the time it launched, there might be nothing left to talk to. If every satellite is jammed, every ground station is a crater, and every radio frequency on Earth is scrambled, this missile still has to hit its target. That was the entire design philosophy. The weapon has to function in the one scenario where everything around it has already failed. So the team at MIT's Instrumentation Laboratory built a brain that needs no help from the outside world. And 60 years later, the Air Force still hasn't found a reason to replace it. The NS-50 guidance computer uses an inertial measurement unit, gyroscopes and accelerometers measuring every moment in 3 dimensions from the millisecond of launch. It knows where it is because it knows exactly where it started and has tracked every acceleration, every rotation, every vibration since liftoff. Pure internal math, no external reference. Think of it this way. Close your eyes in a moving car and try to feel when the car turns left. That's inertial navigation. Except this system does it across 4,200 miles through the vacuum of space at 23 times the speed of sound and lands within the length of a football field. Using a processor your phone could outperform 1,000 times over. Sometimes brute computing power isn't the point. Precision is. After burnout, the post-boost vehicle separates from the spent third-stage motor. The Air Force calls it the bus. Small thrusters fire in bursts measured in milliseconds. Final trajectory adjustments so precise they'd be invisible to the naked eye. The Minuteman III was originally designed to carry 3 independent warheads on this bus. Multiple independently targetable reentry vehicles. MIRVs, 3 warheads, 3 different targets, 1 missile. Under current arms control treaties, each missile carries a single reentry vehicle. 1 cone, 1 target. But the bus still works the same way it always did, including this special party trick. Before the reentry vehicle separates, the bus deploys penetration aids, decoys. Lightweight cones shaped and coated to reflect radar exactly like a real warhead. Chaff clouds that bloom across miles of trajectory, filling a defender's tracking screen with hundreds of returns that all look identical. Mylar balloons inflated to the radar cross-section of a nuclear cone. Absurd in concept, devastating in practice. In the vacuum above the atmosphere, a balloon and a warhead fall at the same speed. No air resistance to sort the real from the fake. A defender staring at this cloud has seconds to decide which dot to shoot at. Pick wrong and you've wasted a $50 million interceptor on a balloon that costs less than a bicycle. The reentry vehicle separates from the bus. It's all alone now. A cone of hardened metal and no engine, no fuel, no communication. Just the math the NS-50 calculated before the third stage burnout and the laws of physics doing the rest. Circular error probable, 120 meters, 394 feet. After crossing more ocean than separates New York from Berlin without a single external navigation signal, this weapon lands inside an area smaller than a city block. And here's where the president comes back in. Every Minuteman III test requires direct presidential authorization. This is not routine maintenance. When a Minuteman leaves the ground at Vandenberg, every adversary with radar coverage knows within seconds. Russia tracked this launch within seconds. So did China. North Korea, too. That's not a side effect. That's the point. The chain of command connects, the crew executes, the weapon performs. America's adversaries saw it before the missile cleared the silo. Russia's Tundra satellites, parked in highly elliptical orbits specifically designed to stare down at North American launch sites, detected the infrared bloom of first-stage ignition within seconds. Automated alerts fired to the National Defense Management Center in Moscow. Officers pulled up trajectory projections, tracking the azimuth toward the Central Pacific, not toward Russia. Not this time. China's early warning constellation picked it up moments later. So did anyone else with a halfway decent infrared sensor pointed at the right patch of California coast. Every one of them ran the same calculation, arrived at the same conclusion, and kept watching anyway. Because the point of a test isn't just proving you can launch, it's making sure everyone else knows you did. The reentry vehicle is now falling toward the Central Pacific at 15,000 miles per hour. In about 90 seconds, it's going to hit the atmosphere. And when it does, the laws of physics that carried it this far are about to try to destroy it. The vehicle slams into the upper atmosphere at Mach 23, and the air can't move out of the way fast enough. It compresses so rapidly, it turns to plasma, a sheath of superheated ionized gas wrapped around the cone like a cocoon made of fire. 6,000 degrees Fahrenheit on the exterior, hot enough to melt titanium. The heat shield handles this the only way physics allows. It tears apart. The ablative coating burns away in layers, each molecule vaporizing and carrying heat with it so the vehicle inside doesn't have to absorb it. The shield protects the warhead by sacrificing itself, one fraction of a second at a time. Underneath that disintegrating shield, the vehicle itself is built for exactly one job: survive the trip. The structural shell is a carbon-carbon composite cone, the same family of materials that line the space shuttle's nose cap. Behind it, the physics package mounts on shock absorbers rated for the deceleration loads of atmospheric reentry, forces that would compress a human spine to half its length. The electronics are potted in resin to keep components from vibrating apart at frequencies no ground test can perfectly replicate. Every gram is accounted for, every material chosen for a specific thermal, structural, or ballistic reason. Nothing is decorative, nothing is redundant, and nothing inside this cone has any idea whether it's carrying a test instrument package or a W-87 thermonuclear warhead. The engineering doesn't care. The physics are the same either way. That plasma sheath also cuts every line of communication. No radio signal penetrates ionized gas at these temperatures. The vehicle is falling blind and deaf. Guided by nothing except trajectory math, the NS-50 ran 20 minutes and 300 miles ago. If that math was wrong by a fraction of a degree, nobody can fix it. Nobody even knows until impact. There is no second chance. Below, the Ronald Reagan Ballistic Missile Defense Test Site inside Kwajalein Natal is waiting. A ring of coral islands in the middle of the Pacific loaded with more tracking equipment per square foot than almost anywhere else on Earth. Radar arrays, high-speed cameras, infrared sensors, and telemetry receivers aimed at a single patch of sky. They built this place for exactly this moment. When that reentry vehicle comes screaming through the atmosphere, dozens of systems capture every millisecond of its descent. The cone carries no nuclear warhead. Instruments and telemetry packages ride where a W-78 or W-87 thermonuclear device would sit, each capable of destroying an area the size of a major city. For this test, every sensor inside it is recording data that engineers will spend months pulling apart. The flight is the test, the data is the product, and the data answers the question the Air Force needs answered. Can this specific missile, pulled from an operational silo, fueled years ago, its guidance system dormant through Montana winters, still perform as designed? If not, the 399 identical missiles sitting underground right now have the same problem. And the nuclear deterrent that has prevented the worst day in human history since 1945 has a crack in its foundation. 30 minutes after two officers turn their keys in an underground capsule in California, the reentry vehicle impacts within 120 meters of the designated target zone. Guidance accurate, systems nominal, flight profile match projections. The data transmits to Air Force Global Strike Command, United States Strategic Command, and the White House. An officer at Malmstrom Air Force Base in Montana just proved the U.S. military can receive a presidential order, authenticate it, turn a key, and 30 minutes later, a reentry vehicle hits a target 4,200 miles away within the length of a football field, guided by math from the 1960s, powered by fuel poured years ago, navigating alone the entire way. And every U.S. adversary with a satellite just watched it work. If you want to see the world's most powerful bomber do something similar, watch this video now. Bye for now.